Recall, we had defined the computation C of a PDA m is equals to k summation tau delta S A on a string W is in an accepting computation when if and only if the computation starts with the initial configuration. What is the initial configuration? At initial state with the string W, stack empty, for multiple yields generates q epsilon epsilon, where q is the final state, input is consumed, stack is empty. A computation C on M halts if and only if at least one of the following conditions hold. So, when it halts, either when the C is in an accepting computation or C ends in a configuration from which there is no transmission in delta that can be taken. So, it is in a configuration, but I do not have any other transitions to proceed further. At that time it halts. M halts on string W if and only if every computation of M on W halts, and if M halts on W and does not accept, then we say that M rejects the string W. For every context free language, we have already proven that there exists a pushdown automata M such that L of M is equals to L. So, we have seen, we have written the context free grammars. For the same context free grammars, we have written the pushdown automatas, and hence we have proved that there exists a PDA for each context free language. It may be deterministic or it may be non-deterministic. Suppose that we would like to be able to examine a string and decide whether or not it is in L. Examine a string that is in L and creates a parse tree for it. Examine a string that is in L and create a parse tree for it in time that is linear in length of the strings. Examine a string and decide whether or not it is in the complement of the language. So, all these can be done in the regular languages. For every regular language L, there exists a minimal deterministic finite state machine that accepts it. That minimal DFSM halts on all the inputs, accepts all the strings that are in L and rejects all the strings that are not in L. So, we have seen, given a context free language, how to design a FSM, given a language, how to design a FSM for that. So, it can be either deterministic or non-deterministic. If it is non-deterministic, we have an algorithm to convert into deterministic, and then given a deterministic FSM, we can go for minimalizing that DFSM by using minimization algorithm. And this DFSM, if the string belongs to that particular language, accepts, else it rejects. But so, this was the case in regular languages, but the facts about the context free grammars and pushdown automatas are different from the facts about the regular languages and FSMs. It is basically because of three problems, and they are: there are context free languages for which no deterministic pushdown automata exists. So, we say deterministic pushdown automata is a subset of non-deterministic pushdown automata. Not all deterministic pushdown automatas are non-deterministic. Given a context free language, there are some languages which are deterministic and some which are non-deterministic. So, there are context free languages for which no deterministic PDA exists. This is one problem. Another, if it is possible that a PDA may not halt or not even finish reading its input. So, this is the major critical problem with the PDA. The condition is it may not halt or even it may not finish reading its input. So, we will see the examples for each of them. However, for an arbitrary PDA M, there exists M dash and halts and L of m dash is equals to L of m. So, this is the second problem. And the third is there exists no algorithm to minimize a PDA. It is undecidable whether a PDA is minimal. We can see there in FSM we minimize the deterministic FSM. We have an algorithm, so it is decidable. But here in PDA we do not have any algorithm as such. So, minimizing a PDA is a undecidable problem. So, out of these three problems, so let us consider the second problem by an example. Let M be a PDA that accepts some language L. Then on input W, if W belongs to L, then what happens? The M will halt and accept. But if W does not belong to the language, then M will not accept W. It is possible that it will not reject it either. Understood? If the W belongs to L, then it will halt and accept. If it does not belong, then that string is not accepted, but even it is possible that it will not reject it either also. For example, say summation having the string A, and this is a push down automata designed for this language. Now, if I want to derive string A, then the possible computations are start with initial state. So, the initial state of this PDA is 1, input string is A, stack symbol is epsilon. 1 A epsilon. So, you can see here from 1 to 2 with an epsilon transition, without considering the input symbol, stack symbol, it is just pushing A into the stack and moving from state 1 to state 2. So, from state 1 to state 2 without consuming A. So, A as it is, push A into the stack. So, now the stack content is A. So, this is the yield 2AA obtained from 1A epsilon. Next, when I am at 2AA, that is at second state, you can see here input is A, stack topmost element is A, 2AA. Then what to do? Pop the topmost element of the stack and reach the final state. So, from state 2 it will go to state 3, where 3 is the accepting state, input is consumed, stack is empty, hence the string A is been accepted. So, this is simple. Given W which belongs to L, it will halt for that particular string and accept it, because that string belongs to that particular language. Now, take the same PDA and take any other input except A, because A is being accepted by that particular PDA. So, we will take L of m is equals to AA as the string. So, when we go for deriving it, so first start state is A, input string is AA and stack is empty. So, at the first yield without consuming any input, so straight away it will go from state 1 to state 2 and pop the push A into the stack. So, from state 1 it will go to state 2, input is not consumed. So, it is as it is AA, and now what we did, 1 A is pushed into the stack, and now we are at 2 AA. Now, again if you can see here 2 without consuming the input, irrespective of what is there in the stack, push A into the stack and go to state 1. So, if I go for selecting this transition, then from state 2 to 1, input as it is, push 1 A into the stack. So, it got 2 A's in the stack now. So, again 1 AA. So, again we will go for this transition from 1 to 2. So, I got from 1 to 2, input as it is, push 1 A. Now, instead of 2 A's in the stack, we have 3 A's. Again 2 to 1, input as it is, stack symbol is A, 3 A's now added with 4 A's. and so on. So, M will never halt because of one path. So, this path never ends. So, from 1 to 2, back from 2 to 1, this is a path which never ends, and none of the paths except. So, from this derivation there is no path which accepts the string, hence the string is rejected, whereas it never halts. So, this is an example wherein we discussed a string which does not belongs to the language never halts. So, what is the solution? For this type of problem in non-deterministic finite state machine, we have two choices: converting NDFSM to an equivalent DFSM by using NDFSM to DFSM algorithm. So, we have already used this algorithm in order to convert NDFSM to DFSM, that is non-deterministic to deterministic finite state machine. So, this eliminates the problem which we have faced recently in the Pushdown automata. One more is simulating the non-deterministic finite state machine using NDFSM simulate. So, this algorithm also we have used to simulate NDFSM. So, these are the two solutions for the problems faced in the PDA, for which we have in finite state machines, for non-deterministic finite state machines. But you can see here, neither of these approaches work on PDAs, because we do not have any algorithms as such in the PDAs. There may not even be an equivalent deterministic pushdown automata also. So, this is a major drawback in the PDA, but we can have a solution which falls in two classes. One is the formal ones that do not restrict the class of the languages that are being considered. So, here what we do is we go for converting the grammars into normal forms like Chomsky normal form and Gribach normal form. So, how to convert into Chomsky normal form we have seen in the previous session. So, one more solution is practical ones that work only on a subclass of the context free languages, wherein we go for using the grammars in natural forms. So, this is about non-determinism and halting. Now, coming to alternative equivalent definition of a PDA. Actually, if you go through a number of books on ATC, we see different alternative definitions of PDA, but all are equivalent with each other. So, in this textbook, other alternative definitions defined are allow M to push and pop and push any string in the tau star. It means what? So, till now what we have seen, we push an element into the stack and pop an element from the stack. Other alternative definitions are you can push and pop a string of elements into the stack which belongs to the stack symbols. This is one alternative definition. Another is M may pop only one single symbol at a time, but may push any number of them. So, if I want to push one or more number of symbols, I can push into, but when I want to pop, I can pop only one, the topmost element symbol from the stack. So, another alternative is M may push and pop only one symbol at a time. Either it can push or pop only one symbol. So, these are the different alternative definitions of the PDA. The one which we have defined in this course is M accepts its input W when and only when it finishes reading the string, that is the string input string is empty, it reaches the accepting state and the stack is empty. When it reaches these three conditions, we say that the machine accepts the input string W. There are other alternative definitions of PDA. Some are PDA by final state. So, what do you mean by PDA by final state? It will accept if when the input is been consumed, it has reached the final state, but regardless of the content of the stack. It means the input is consumed, it has reached the final state. So, we are not considering what is the content of the stack, whether there is this content in the stack or the stack is empty. Irrespective of that, if the input is consumed and if I reach the final state, then the string is been accepted. So, such type of PDA is called as PDA by final state. Another definition, PDA by empty stack. It means it will accept if input is consumed and stack is empty, irrespective of in which state it is. So, whether it is in intermediate state or it is in final state, irrespective of that, if the input is consumed and the stack is empty, then the string is accepted. Such type of PDAs are called as PDA by empty stack. So, all these definitions whatever we defined are equivalent in the sense that if some language L is accepted by a PDA using one definition, it can be accepted by some PDA using each of the other definitions. What do you mean by this? Say suppose, if some language L is accepted by a PDA by final state, then it can also be accepted by a PDA by final state and empty stack, both. If I have a PDA with only final state, then I can have its equivalent PDA with both final state and empty stack. Similarly, if some language L is accepted by a PDA by final state and empty stack, by both final state and empty stack, that can also be accepted by a PDA by final state. So, this we can prove by showing algorithms that transform a PDA of one sort into an equivalent PDA of the other sort. So, let us take an example of proving wherein to show that they are equivalent, given a PDA M that accepts by accepting state and empty stack, construct a new PDA M dash that accepts by accepting state alone, where L of M dash is equals to L of M. That is, given is what? A PDA accepting state and empty stack, and what we are supposed to create is a PDA by accepting state alone, where both are equivalent. One more, given a PDA M that accepts by accepting state alone. So, I have accepting state alone PDA. Now, I have to create its equivalent PDA consisting of what? Which accepts by accepting state and empty stack, where L dash is equals to L of M, and hence can prove that M dash and M accept the same strings. So, let us go for designing both of these types and then prove that both are equivalent and they accept the same string. So, consider the first case wherein the input is accepting by final state. How we will define the PDA for this? Define a PDA M is equals to K summation tau delta SA, which accepts if when the input has been consumed, M lands in an accepting state regardless of the contents of the stack. Whatever may be the content of the stack, if the input is consumed and it has reached the final state, then the string is been accepted. So, how we will define it? M except if the computation is, it is at the initial state where it starts with start symbol S for the given string W, stack empty. For multiple yields, it reaches state Q, where Q is the final state. Input is consumed, but stack may have some stack symbol, that is gamma. So, when we design this M dash will have a single accepting state, that is Q. In the previous accepting by final state alone, you may have one or more number of final state, but when you convert it, you will be having only one single accepting state q a. The only way for m dash to get to q a will be to land in an accepting state of m when the stack is logically empty. So, when do you say that the stack is logically empty? In the previous session we have seen, since there is no way to check that the stack is empty, what we did? M dash will begin by pushing a bottom of stack marker hash into the stack before doing anything. So, when we have hash on top of the stack, then we say that the stack is logically empty. So, let us go through the algorithm. Initially, I have let your machine existing input machine m be m dash, create a new start state s dash. Why this new start state? Because I have, before doing anything, I have to push hash into the stack. So, for this, these two statements. So, create a new start state s dash, add the transition s dash epsilon epsilon, a simple epsilon transition from s dash to s to push hash into the stack. Third step, for each accepting state a in m, for all the accepting states, I must add a transition from that accepting state, input empty, stack topmost element showing the logical empty stack, then go to the final state q a and pop the topmost element of the stack, that is hash, showing that the stack is empty, and make q a the only accepting state in m dash. Now, you can see here, this is an example of, what is this example of? It is a deterministic push down automata for balancing the parenthesis. So, how we obtain this PDA we have discussed in the previous sessions. Since the first string in the parenthesis, balancing the parenthesis is epsilon, so initial state is the final state, we have only one state yes. Whenever you come across a opening parenthesis, irrespective of what is there on the stack, push that opening parenthesis into the stack, and whenever you come across a closing parenthesis, then this must be paired with an opening parenthesis which must be at the top of the stack. If there is a match, then pop the opening parenthesis from the stack, and once you are in final state, input is consumed and the stack is empty, then this string will be accepted, which are of balanced parenthesis. So, now I have this. So, this must be converted. So, to convert acceptance by final state alone, you can see here, initially let m dash is equals to m. So, this m as it is here, then create a new start state s dash. So, I have a new start state s dash, wherein we have a transition from s dash to the old start state s with the transition epsilon epsilon, and what to do? Hash to be inserted into the top of the stack. Then all the transitions of the PDA as it is will go on. For each accepting state A in M, so which is the accepting state A here? Only one state is the accepting state, that is yes. So, from this yes, I must have a transition to a accepting state QA. So, from yes, I have a transition to QA. And what is the transition? From A epsilon hash, yes, epsilon hash. So, pop the hash. So, epsilon moving from S to QA. And now what? Last step is make QA the only accepting state in M dash. So, previously this S was the accepting state. After having this transition from S to QA, now S is an intermediate state and QA is the only final state. So, this is a PDA converting from both empty stack and final state to only final state. it is easy to see that M dash lands in its accepting state QA if and only if M lands in some accepting state with an empty stack. Thus, M dash and M accept the same string. The other way now, that is acceptance by final state and empty stack. What is the input? Acceptance by final state alone. What must be the output PDA? PDA must be having both final state and empty stack. So, to construct this, we need an algorithm which is almost similar to the algorithm previously discussed. So, initially let M dash be M, create a new accepting state F. For each accepting state A in M, do what to do? Add a transition A epsilon epsilon to F epsilon and make F the only accepting state in M. For each element G in tau, add a transition to M dash F epsilon G to F epsilon. So, we will quickly go through. So, this was a PDA by acceptance by final state alone, which we just discussed. Now, this must be converted into acceptance by both final state and empty stack. So, to perform this, so what is the steps written here? Create a new M dash is M, create a new final state, add a transition. So, you can see here this PDA as it is. Now, we are creating a new final state and we add a transition from this final state to this final state. Now, previously QA was a final state, now F will be the final state and this will be the intermediate state. We will be having an epsilon transition from this QA to F. So, you will be having a epsilon transition from the previous final state to the current final state F. Then, for every element G in tau, add a transition to M dash, that is F epsilon G as F epsilon. So, which all elements are there in the tau in this example? So, only we have opening parenthesis as a tau symbol. So, we have one transition as a self loop for F, wherein input is empty, whereas the tau symbol is opening parenthesis. Then what to do? Pop the stack. So, you can see here by this state at QA, it has already reached the final state here, but we did not check for emptying the stack. So, what we did? We took one epsilon transition to F, wherein we popped an element from the stack, and then if any elements present in the stack, which elements will be there in the stack? All the stack symbols. So, for all the stack symbols, I will write a self loop for the same final state in order to pop the symbol. Hence, this self loop will pop all the symbols present in the stack and make the stack empty. So, hence at state F, input is consumed, stack is empty, it has reached the final state, hence the string is accepted. In other words, if and only if M accepts, go to the only accepting state of M dash and clear the stacks. The only accepting state here is F, wherein we are clearing the stack. Thus, M dash will accept by accepting state and empty stack if and only if M accepts by accepting state. Thus, M dash and M accept the same strings. So, what we did? Given a PDA that accept by accepting state and empty stack, we created a new PDA that accepts by accepting state alone. So, this we have done by considering the balanced parenthesis example. Second, given a PDA M that accepts by accepting state alone, constructs a new PDA that accepts by both accepting state and emptying state, again where L of m dash is equals to L of m. So, for this also we have considered an example. Hence, we proved that m dash and m accept the same strings. Some other alternatives at last. What are the alternatives that are not equivalent to the PDA? So, till now what we have told about the PDA, PDA is nothing but a FSM wherein we add a single stack. So, we define a PDA to be a FSM to which we add a single stack. There are many more variants, in that two variants of these definitions are, each of which turn out to define a more powerful class of a machine. The first variant, in place of stack we go for inserting queue. So, add a first in first out queue in place of a stack. Such machines are called as tag symbols or post machines. Second variant consists of, in place of one stack we go for using two stacks. So, add two stacks instead of one. The resulting machines are equivalent in computational power to Turing machines. So, these are some alternatives wherein we discussed FSM having only one stack. Instead of stack we may have queue, or instead of single stack we may have two stacks, wherein the more powerful classes of machines are being built, and those machines are called as post machines or Turing machines.